So, firstly let me start with a few more counting methods. So, one of them is the so called the injection principle. Okay, so these principles are based on counting the number of functions from one finite set to another finite set, depending upon the nature of the function. That means, it can be a one-to-one function or it can be an on-to function, etcetera. So, depending upon that you will have the number. So, if those numbers are matching, these are used for doing various counting problems. So, let me firstly talk about the injection principle. So, let A and B be finite sets if there exists a one-to-one mapping f from A to B, then the number of elements of A is less than or equal to the number of elements of B. So, this is something very simple to understand. For example, I just make a diagrammatic representation. I have certain number of elements here, and so each one of them is a one-to-one function. So, naturally you can see that each element is mapped to a member here. So, if there are some members left out, then the cardinality of B is always more than or equal to the cardinality of the set A. So, this is only less than or equal to. So, if we put one additional restriction on this, then you have the direct counting. So, that is called the bijection principle. Or we call it BP. So, let A and B be finite sets if there exists a bijection f from A to B, that means one-to-one and on-to mapping, then the cardinality of A is same as the cardinality of B. We can also talk about many times there are problems in which we are asked to find out the number of divisors of a given natural number. So, here what we do, we can actually consider a similar thing, that is by bijection method. Let us consider this. So, applications of fundamental theorem of arithmetic, usually we call it FTA in short, for finding the number of divisors of a natural number. What is the fundamental theorem of arithmetic? I think all the students are familiar with this. That is, every natural number n greater than or equal to 2 can be factorized as n is equal to p 1 to the power m 1, p 2 to the power m 2, p k to the power m k. For some distinct primes p 1, p 2, p k, and some natural numbers m 1, m 2, m k. Such a factorization is unique if we disregard the order of primes. That means, in place of p 1 to the power m 1 into p 2 to the power m 2 etcetera, if we interchange the order, firstly we put p 2 to the power m 2, then we write p 1 to the power m 1, then it does not make any difference, then this factorization is considered to be unique. This is one of the fundamental results in number theory. In fact, it was known at the time of Euclid, who proved it for one elementary case, and in the full form it was proved by Carl Friedrich Gauss in 1801. Now, let us see, this can be used for finding out all the divisors. So, I will show you the application of the bijection principle here. Find the number of divisors of say 72. So, 72 can be written as 2 cube into 3 square. So, by factorization theorem, this is the unique representation of this. So, if x is a divisor of 72, then x can be written in the form x is equal to say 2 to the power a into 3 to the power b, where a belongs to the set 0, 1, 2, 3 and b belongs to the set 0, 1 and 2. So, now let us consider, let A be the set of divisors of 72 and B be the set of this tuples A B, where A can take values 0, 1, 2, 3 and B can take values 0, 1, 2. Then naturally, you can see that there is bijection from A to B. In fact, we can display this full thing. In fact, we have function, you can write like this. See this f, if I choose say 0, 0, that means A is 0, B is 0, you get exactly 1. So, I have to say it is like this, f 1, that is the divisor 1 is corresponding to A is equal to 0, B is equal to 0. If we consider the divisor 2, then that is corresponding to A is equal to 1 and B is equal to 0. Similarly, if I consider divisor say 3, then that is corresponding to A is equal to 0, B is equal to 1. If I consider divisor 4, then that is corresponding to A is equal to 2, B is equal to 0. If I consider divisor 6, then that is corresponding to A is equal to 1, B is equal to 1. Then if we consider the divisor 8, then that is corresponding to A is equal to 3, B is equal to 0. If we consider 9, then that is corresponding to A is equal to 0, B is equal to 2. If we consider 12, then that is corresponding to A is equal to 2 and B is equal to 1. If we consider say 18, then that is corresponding to A is equal to 1 and B is equal to 2. If we consider 24, then that is corresponding to A is equal to 3, B is equal to 1. 36 if we consider, then that is corresponding to 2 2, that is 4 into 9, and finally, F 72 is corresponding to 3 2. So, if you look at 1 2 3 4 5 6 7 8 9 10 11 12, all the 12 elements of the set A are corresponding to total number of 12 elements of the set B. So, it is a 1 1 on 2 map, that is a bijection. So, by the bijection principle, the number of elements of A is same as the number of elements of B, that is 12. There are total 12 divisors of the number 72. So, now let me just give some simple applications to some slightly larger numbers. So, we look at find the number of divisors of say 12,600, 31,752 or 55,125. So, let us look at this. 12,600 can be factorized as 2 cube into 3 square into 5 square into 7 to the power 1. So, any divisor is of the form 2 to the power A, 3 to the power B, 5 to the power C and 7 to the power D, where now you see A, B, C, D where they belong to. A can be any number 0, 1, 2, 3, B can be any number 0, 1, 2, C can be any number 0, 1, 2 and D can be any number 0, 1. So, mapping F defined by F of x is equal to A B C D, then this is a bijection from A, that is the set of divisors of 12,600 to the set B, which is nothing but the collection of 4 tuples, where A is between 0 to 3, B is between 0 to 2, C is between 0 to 2 and D is between 0 to 1, they are integers. Now, how many elements are here? Cardinality of B is here you have 4 elements, here you have 3 elements, here you have 3 elements and here you have 2 elements. So, this is nothing but exactly 72. So, the number of divisors of 12,600 is 72. Similarly, let us consider say 31,752. This number is 2 cube into 3 to the power 4 into 7 square. So, if we consider x as 2 to the power A into 3 to the power B into 7 to the power C, then A, B, C will belong to 0 less than or equal to B less than or equal to 4, 0 less than or equal to C less than or equal to 2. So, cardinality of B is 4 into 5 into 3, that is 60. So, that is the number of divisors of this. In a similar way, if I consider 55,125, then that can be expressed as 3 square into 5 cube into 7 square. So, the cardinality of B in this case will become 3 into 4 into 3, that is 36. So, in general, then we can state the following theorem as an application of this fundamental theorem of arithmetic and the bijection principle. We have the following result on the number of divisors of a given natural number as an application of FTA and the bijection principle. I state it in the form of a theorem. If n can be expressed in the form p 1 to the power m 1, p 2 to the power m 2, p 3 to the power m 3 and so on p k to the power m k, where n is greater than or equal to 2, where p 1, p 2, p k are distinct primes and m 1, m 2, m k are natural numbers, then the number of divisors of n is given by m 1 plus 1 into m 2 plus 1 and so on up to m k plus 1. So, this was one application of the bijection principle, which is useful in counting the number of divisors of a natural number. I further look at some more counting methodologies. So, they are called occupancy principles, that is putting a number of objects into a number of cells or putting a number of balls in a number of boxes. So, this has wide variety of applications when we are seating people, when we are arranging some sort of queues, etc. So, in general they are called occupancy problems. So, let me look at this. The number of ways of distributing are identical balls into n distinct boxes. N r plus n minus 1 choose n minus 1, which is same as r plus n minus 1 choose r. So, let me specify the problem. So, as I mentioned, you can have r identical objects. So, which we can call r identical balls, and they have to be placed in r distinct cells or n distinct boxes, etc. So, this number is given by r plus n minus 1 choose n minus 1. Let me give a proof of this. Let us represent r balls by r stars. So, this is just a way of representing. Sometimes we write it as r apples and in between we are placing oranges and so on. So, I am just putting the simplest notation stars. Okay. So, this r balls, they are identical. So, they can be treated as this thing. and indicate this n boxes by n spaces between n plus 1 vertical bars. Let me explain it. So, suppose I have two boxes. So, if I put three vertical bars like this, then this acts as a box, this acts as a box. Similarly, if I have say 3 boxes, then I make 4 bars. So, now what is happening is that the stars are in between, because we are placing this r stars, that is r identical balls into these boxes. So, it is something like this. You have r stars here and you have n plus 1 vertical bars. Again, out of this vertical bars, this there has to be one start and one end. So, in between you can have n minus 1 vertical bars and r star. So, that is r plus n minus 1. Out of that, n minus 1 things have to be chosen, or you can say r things have to be chosen. Both are identically true. So, it becomes r plus n minus 1, choose r, or r plus n minus 1 c n minus 1. So, this arrangement has vertical bars at the beginning and at the end. Remaining n minus 1 bars and r stars can be arranged in n plus r minus 1, choose r, or n plus r minus 1, choose n minus 1 ways. Now, in this arrangement there can be possibility that some box is empty. Now, suppose we put some additional restriction that no box is empty, then what will happen to the number of possibilities? Let us look at that. So, that is a variation of this occupancy problem. The number of ways of distributing r identical balls in n distinct boxes, so that no box remains empty. So, that is r minus 1 choose n minus 1, which is also r minus 1 choose r minus n. Here r is greater than or equal to n. Let me prove this statement also. If there are no empty boxes, then no two vertical bars can be adjacent. For example, in this I have made these two bars adjacent and there is no star in between. So, this possibility will not be there. So, the r stars have r minus 1 spaces, of which n minus 1 have to be occupied by vertical bars. that is how many vertical bars, that is n minus 1. So, this can be done in r minus 1 choose n minus 1, that is r minus 1 choose r minus n ways. So, I have given solution to two occupancy problems. One is the number of ways of distributing r identical balls in n distinct boxes, that is r plus n minus 1 choose n minus 1, and if we put the additional restriction that no box is empty, then this number becomes r minus 1 choose n minus 1. So, let us look at an application of this. Eleven persons including 3 specific persons, say P, Q, R. Are to be seated on 11 seats. So that P, Q, R do not occupy adjacent seats. In how many ways this can be done? So, out of this 11 persons, 3 persons are specific on which we are putting some restriction. So, what we do? We firstly place 8 persons. Okay. So, first we arrange 8 persons in 8 factorial ways. That is, we have excluding P, Q and R. So, you can see like this person 1, 2, 3, 4, 5, 6, 7, 8. Now, how many places are left out? We have now 7 places in between, and on the side also we have 2 places. So, there are total 9 places in which we can put this P, Q and R. Okay. So, this can be done in how many ways? In 9 remaining places, 3 seats can be placed in 9 P 3, that is 9 into 8 into 7 ways. So, the total number of possibilities becomes 9 into 8 into 7 into 8 factorial, which is of course a large number. Six distinct symbols are transmitted through a communication channel. A total of 18 blanks are to be inserted between the symbols with at least 2 blanks between every pair of symbols. In how many ways symbols and blanks can be arranged? Let me just repeat the problem again. There are 6 different symbols which have to be transmitted through a communication channel. Now, in between the symbols we have to insert 18 blanks, such that between every pair of symbols at least 2 blanks are there. Then in how many ways this symbols and blanks arrangements can be done? So, let the 6 symbols be say S 1, S 2. So, S 1, S 2, S 3, S 4 and S 5 and S 6. Okay. Now, we have this spaces here. Okay. This blanks have to be inserted necessarily between the symbols only. So, between the symbols you have 5 places. So, this can be considered as a problem of placing 18 identical balls, that is the blanks, we can treat them as the identical balls into 5 boxes. Now, first thing is that it is written that between every pair at least 2 blanks have to be there. So, firstly we put 2 blanks there. So, first we choose 2 blanks each. So, from 18 identical things, if we choose 10 identical things, then we are left with. So, since all of them are identical, this choosing has no meaning, basically it means one way only, in one way. Now, remaining how many are there? 8 blanks are left out. Now, remaining 8 blanks can be placed in 5 boxes in 8 plus 5 minus 1 C 5 minus 1, that is 12 C 4 ways. So, you can see this problem we have reframed as a problem of placing identical balls into distinct boxes. Plus, we had some additional condition here that between every pair of symbols there are 2 blanks. So, that part we took care by separately putting them. So, 10 blanks were selected and put there. Since they are all identical, then the number of ways of choosing that is 1 only. Now, the remaining becomes r plus n minus 1 C r minus 1, and we have done that thing here. Find the number of non-negative integer solutions to x 1 plus x 2 plus x 3 plus x 4 is equal to 10. Now, this can be considered as the problem of distributing 10 ones there are 10 ones. So, x 1 can be 0 because we are putting non negative integer. So, x 1 can be 0 1 to 10, x 2 can be 0 1 to 10 and so on. So, basically it is a problem of distributing ones. So, there are 10 distinct identical ones which have to be placed into 4 distinct boxes. So, this is same as distributing 10 identical balls in 4 distinct boxes. So, that is n plus r minus 1 C n minus 1, that is 13 C 3. So, we can actually extend this result to writing down an equation in n unknowns. So, consider the equation x 1 plus x 2 plus x n is equal to r, where r is a non-negative integer. Let me call this equation number 1. Then the number of non-negative integer solutions to equation number 1, that will be r plus n minus 1 C r, that is r plus n minus 1 C n minus 1, because this is same as the problem of distributing r identical things into n boxes. If we put the restriction that x i's are greater than or equal to 1, that means non-zero, the number of positive integer solutions to 1, that is r minus 1 C n minus 1 or r minus 1 C r minus n. Ten letters are to be selected from 5 vowels with repetitions allowed. Okay, 5 vowels are A, I, E, O, U, and we have to select 10 out of that. That means, all of these numbers can be repeated. So, first thing is, in how many ways this can be done. Second is, what is the number if each vowel has to be selected at least once. So, here if you see the solution here, 10 plus 5 minus 1 C 10, that is same as 14 C 10, that is 1001. In the second case, it is 10 minus 1 C 10 minus 5, that is 9 C 5. Find the number of ways of distributing are identical objects into n distinct boxes such that box 1 can hold at most one object. Let us give the argument for this here. So, box 1 can have either no object or one object. So, if box 1 has no object, then the problem is to place r identical things into n minus 1 distinct boxes. Then we can distribute r identical objects in n minus 1 boxes in r plus n minus 2 C r ways. And if we place, if box 1 has one object, then we can distribute r minus 1 identical objects in n minus 1 boxes in r plus n minus 3 C r minus 1 ways. So, by addition principle, the total number of ways is r plus n minus 2 C r plus r plus n minus 3 C r minus. Earlier we have considered the choosing of or you can say arranging of distinct items out of a list of distinct items in a particular way. So, either unordered ways or ordered ways, that gave rise to the concept of permutation and combination. Now, this can also be considered as the distribution of balls problem into the boxes, if we consider distinct balls and distinct boxes, etc. So, let me give these concepts also. So, now we consider distribution of distinct objects into distinct boxes. The number of ways of distributing r distinct objects into n distinct boxes such that each box can hold at most one object. So, that will be n p r. Let me give the proof of this here. So, here you can see the difference from the previous one, that earlier we had taken identical objects. Now, we are taking distinct objects. Boxes were distinct earlier also, now are there same. So, this is actually nothing but the ordered arrangement. Let me give a formal proof of this. So, you have say n distinct boxes. Now, you are saying that you will put r objects into this. So, this is same thing as like, because each box can have at most one object. So, here r is less than or equal to n here. So, you can have say here, here etcetera. What wherever you put it is nothing but one arrangement of r things out of n. So, this can be simply considered as number of r ordered arrangements of n distinct items, that is nothing but n p r, basically from n. So, basically what you are doing is that you are choosing r boxes here out of n, and here you are also saying that the number is important, that means in which order we have placed them here. We can give argument like this also. One can argue in the following way also. One can place the first object into any n boxes, then second object into n minus 1 boxes, and so on. So, rth object into n minus r plus 1 boxes. So, the total number of arrangements is nothing but, by multiplication principle, n into n minus 1 and so on up to n minus r plus 1, that is nothing but n factorial divided by n minus r factorial, that is n p r. The number of ways of distributing r distinct objects into n distinct boxes such that any box can hold any number of objects n to the power r. So, here you can see the argument is little bit different. The first object can be placed into any of the n boxes, the second object can be placed into any of the other n boxes, and so on. So, each of r objects can be placed in n possible boxes, that is n into n into n r times, that is n to the power r ways. Another way of counting is the number of ways of distributing r distinct objects into n distinct boxes such that the ordering of objects matters in each box. So, then that is equal to n plus r minus 1 C r into r factorial, that is n into n plus 1 and so on up to n plus r minus 1. So, to resolve this problem, let us first assume that objects are identical. If that is so, then the number of ways of placing these in n boxes is n plus r minus 1 C n minus 1, that is n plus r minus 1 factorial divided by n minus 1 factorial r factorial. Now, if the objects are distinct and the ordering matters, then the total number of orderings of r things is r factorial. If the objects are distinct and the ordering matters, then the total number of orderings of r objects is r factorial. So, the total number of ways is n plus r minus 1 factorial divided by n minus 1 factorial r factorial into r factorial, that is n plus r minus 1 factorial divided by n minus 1 factorial. That is of course, if you simplify this, it becomes n plus r minus 1 into n plus r minus 2 and so on up to, which we can also write as n plus r minus 1 p r. Let me take up another occupancy problem. Suppose there are n 1 identical objects of type 1, n 2 identical objects of type 2 and so on, n k identical objects of type k, where n is n 1 plus n 2 plus n k, that is the total number of n objects are there, out of which n 1 are identical, n 2 are identical and so on, they are all of different type. Then the number of arrangements of these n objects in a row is n c n 1, n minus n 1 c n 2 and so on, n minus n 1 minus n k minus 1 c n k, which is same as n factorial divided by n 1 factorial, n 2 factorial, n k factorial. So, this is actually same as arrangement of n objects in which n 1 objects are alike, n 2 are alike, and so on. So, this is same as n factorial divided by n 1 factorial, n 2 factorial, n k factorial. So, these occupancy problems, they have various applications. We have already seen some problems which are solved using this arrangement, that is, you have distribution of things into different cells, arrangements by taking certain things in a particular order, and so on. So, there are so many problems that can be solved using these concepts. So, right now I conclude my discussion on the permutations, combinations, occupancy problems, and certain principles of counting at this moment.